scratchy this morning. No COVID. I took a test and everything. So I'll take off my mask so that everybody can hear me properly. But this is so you can decide to put on your mask if you want to. Okay. So I let you make the decision. And as Gustavo was just promising you, today we are going to begin to talk about inflationary cosmology. And unlike in the real world, inflation here is going to be the solution to our problems and not the cause of them. And what we're going to be trying to do over the course of this lecture and the beginning of the second is giving you this picture that I promised you, a dictionary between a particular model of inflation and the spectrum of perturbations that are created by that model of inflation. Okay, so we want to go from theory to the spectrum of perturbations, p zeta. Okay? And one of the things we'll show is that classic slow roll inflation does give you a nearly scale invariant power spectrum. We will also discuss, probably not today, but hopefully tomorrow, the influence of things like heavy relics that are present during the course of inflation, whose mass happens to be around the inflationary scale, and that can be thus produced during inflation and thus have effects on the spectrum of perturbations. And I'll put kind of new physics here in quotes. Inflation itself is already new physics, but it's so well established as a theory that so far matches the data very well that we might as well call anything else that we add to it new physics on top of standard inflationary cosmology. Okay? And so the idea, maybe just to give a quick picture of why heavy relics might influence the spectrum of perturbations, is from the following kind of diagram, where I imagine inflation is going on, and so we're looking as a function of t, and we spontaneously, out of the vacuum, we produce a couple of heavy phi particles. They might be off-shell, but then they can decay. Their off-shellness just gives them a little bit of impetus to go into on-shell states. Okay, so we have some sort of production of these guys at some point in time. And the things that they decay to are the lightest things in the game, which would be just the inflaton in this case. So the simplest model, I've got a heavy particle phi, and then I've got the inflaton. And remember that if the inflaton is the only scalar field in the game, that corresponds directly to the zetas, those initial perturbations that we're interested in sort of evolving from the end of inflation towards what we see in the CMB power spectrum. So these are literally the zetas, okay? And now we have, say the end of inflation at some point in time. But now we have a non-trivial 4-point correlation function in these zetas, where that correlation function is sensitive to the nature of the new physics that we just introduced. So if we have a power spectrum that in the absence of big phi is purely Gaussian, then our new distribution over zetas, including phi, is going to have non-trivial endpoint correlators. Okay, so that's the idea of how new physics might influence interesting aspects of the power spectrum of these initial conditions. Okay, so now we'll just step back and start going through the standard classical theory of inflation. And by the end of the lecture today, I want to start getting to the quantum fluctuations of fields in de Sitter space to understand how quantum fluctuations at early times evolve into the perturbations that we observe at later times. Okay. We are pretty sure that inflation is the answer to why the universe is so homogeneous, isotropic, and as we referenced in the first lecture, why there is no spatial curvature, that is, why it's so spatially flat. As John told us yesterday, it can also clean the universe of any things that we don't see today that we should, like maybe very heavy stable relics like monopoles. There are many other things besides monopoles that can sort of spoil what we see right now, this homogeneity and isotropy. For example, if you've got an axion solution to the strong CP problem, when I break the Peccei-Quinn symmetry that leads to that axion in a very big universe, you create all sorts of things like vortices and domain walls that we also don't observe right now. So that would be inconsistent with Big Bang cosmology if there were a temperature that was high above the Peccei-Quinn breaking scale. So we look out, we don't see any axion domain walls, so we've got to throw out the axion solution to the strong CP problem. No, maybe that breaking happened before inflation, and inflation just cleared the universe of all of that stuff. Okay? So, e.g. monopoles. Okay. So interesting story about the backstory of inflation. Henry Tye was working a lot with Alan Guth, and I think it was Henry Tye that sort of suggested that inflation would solve the monopole problem. Then Henry went away for a while back to China, and in the meantime, Alan Guth had to finish the paper, and this contribution to Henry didn't get him on the author list. But he was certainly a part of the story. Okay, and so this is related to the horizon problem, which I'll talk about in a bit more detail now. I meant to stop here. Okay, so just remember, maybe let's recall how inflation solves the spatial flatness problem. We can write an effective Friedmann equation for Hubble squared that, when we plug things in, looks like the following. And let's write our radiation as some initial energy density in radiation at some early epoch in the universe, divided by the scaling that we know will occur with its expansion, plus rho matter over a cubed. And then when you put the curvature term into the metric, the spatial curvature term, there's another piece here that goes like k over a squared. And now we might add one more thing at the end corresponding to a fluid that does not dilute with the expansion of the universe. And so what we see is as the universe expands, if we start at very early times, first this is going to be dominating, then this is going to be dominating, and if I didn't have this, then this would dominate at late times. But if I insert this cosmological constant-like term at the end here, then this will dilute too, and this will be the last fluid standing. Okay? And if you work this out, this is A dot over A equals constant. We know how to solve that equation. It leads to exponential growth of the scale factor. Okay? So this is like a very toy model of something that'll produce an inflationary-like cosmology that could dilute this K factor here. Okay? So that's flatness. And so what inflation is going to be is a story about how to get from an early universe that has a fluid that looks something like this to a universe that doesn't have that fluid anymore at late times. So where I have some sort of early rho lambda effective that is almost constant, that evolves and has some sort of dependence on A that is to just make sure that this is gotten rid of. So we have some rho lambda that is some function of A, and it just has to be a function of A that survives longer than this. Okay? So now let's talk about the horizon problem. And how happily this same hypothesis that solves the flatness problem also solves the horizon problem. So I'm going to be talking now using the coordinates where we're working in conformal time. So let's assume inflation's been going on. We forget about K now. We assume that inflation's going on, K is gotten rid of. All right, so let's just drop that out. So our metric that we're looking at is A tau squared minus d tau squared plus dx squared. And nicely, the metric that's appearing just inside here, inside the brackets, is the Minkowski metric, right? And so this means that we can write space-time diagrams in this metric that have the same kind of meaning that space-time diagrams would in just plain old flat space. All right? The causal structure is easy to understand in these coordinates. So now what we can do is plot sort of the history of the universe as a function of tau and draw our light cones. So we are here, okay? And so what we want to draw is our past light cone. That is the set of all events that can have possibly influenced what we see. Okay, so we just draw some 45-degree angles. Okay, and tau equals 0. In the absence of this kind of stuff here, is the time at which all of these terms are diverging, and you have the Big Bang singularity where everything, the temperature is reaching M Planck if you just naively extrapolate back, okay? So this is the singularity. Okay, and that means there's a time of recombination that I can write across this diagram now. All right. And so now the horizon problem can be stated as the fact that when I say look at two disparate points on the sky, P and Q, at the time of recombination, the past light cones of the points P and Q are small. So here's all of the things very close to the singularity that could have affected what P is doing. And here is the set of all events that could have influenced what we see happening at Q. Because remember, we get a snapshot, right? The photon is telling us what's going on at P. It's telling us what's going on at Q, okay? And now the horizon problem is when we look at the CMB, we get strong correlations between what we see at P and what we see at Q. Why the hell are they correlated if there's nothing in the past history of events P and Q that overlap? So let's write it as delta TP, delta TQ is non-trivial. There are long-distance correlations in the system that have no right being there, given this picture that we've drawn here. And so if you like, this is another fine-tuning problem, but an enormous fine-tuning problem in that I must have to fine-tune the initial conditions over here and here to look correlated, even if they're not, even if there's no physics that could have actually correlated them, okay? It's a little bit similar to the scalar hierarchy problem. If I have a condensed matter system and I have long-distance correlations in that condensed matter system, it means that somebody probably really carefully dialed some knob and tuned it so that the system is at a critical point and long-distance correlations emerge in that system, okay? So it's like fine-tuning the Higgs mass to be 0 so that the Higgs gives long-distance correlations, okay? The standard model is close to a critical point as another way of rephrasing the hierarchy problem. Who put it close to that critical point? Okay, so how do we solve this problem with inflation? So by the way, another way of stating this problem that's often done is similar in that I have some point on the singularity here that where the horizon size is very tiny, the horizon size at the time of recombination is, I think it's about a degree or two on the sky, and here's another degree or two on the sky, and again, the influence of this has nothing to do with the influence of this, and so why are these two patches look like they're in thermal equilibrium even though they're not? These are just two alternative ways of saying essentially the same thing. I like the language of the correlation, but you can pick and choose. Okay, so another way of saying it, how is near perfect thermal equilibrium attained across these causally disconnected patches? Okay, and so one way is some absurd amount of fine-tuning. Another way is to consider alternative histories of the universe that that augment the causal structure that we've seen here, that let us go back further in time to, in this case, it'll be negative tau. So let's see how that happens. So if we write the maximum distance over which I can have correlations, which will correspond as a function of, well, which will be a function of time as the universe evolves. So this is sort of like Dmax right here in this picture, is the size of that patch which is in causal contact. So d max of t, you can write this as a of t times the integral from 0 to t dt prime over a of t prime. Now let's make sense of this really quickly. This is just tau, or c times tau, right? And so that's the sort of distance in proper time, but then I've got to augment by a scale factor a, right? So it's like, you know, the particle is traveling at the speed of light, but the space between where it started and where it finished has expanded by scale factor a. Okay, so that's where the elements in this equation come from. And you can change variables here to make this an integral over a rather than time, which gives us a integral of d log a over a prime, which in this case here will start at 0 and go to a. Oh, no, sorry. Yeah, a starts at 0 no matter what we are, right? So whether I have this picture or some augmented picture, this is going to be fine to write down. This is either the Big Bang Singularity or some alternative beginning of the expansion history. Okay, so now let's look at this integral a little bit and try to see where most of the contribution comes from for a different evolution of the scale factor a. That is, do I get contributions from small a mostly, or do I get contributions from big A mostly? So there are two possibilities in that case, and they depend on, well, how does A prime behave? Does it increase or does it decrease as a function of time? Which is, of course, related to the second derivative of A. So prime here is with relation to the t coordinate, not the tau coordinate, by the way. All right. So let's write down A double prime. A double prime over A, if I just rearrange the Friedmann equations to get just A double prime over A, is going to be minus 1 over 6 m Planck squared rho plus 3p. Okay? But we know now what to do with this if we have some sort of fluid like the ones that are appearing here, and we have some equation of state corresponding to that fluid. And so when we write this out in terms of just the energy density in the fluid, we get 1 plus 3w. Okay? So again, if A double prime is less than 0, then D gets contributions at late times. And for it being greater than 0, gets early time contributions. I don't know why I wrote all that out, but anyway. Okay, but now let's think about ordinary matter.
You wrote smaller than.
Oh, I did, thank you. Very good. Okay, so now what is the sort of boundary between these two different behaviors? It's at a funny value of W. So for W, equal to 0, 1/3, we get convergence at early times, right? So if a w is greater than minus 1/3, if a is finite, as it is now, this integral is convergent. But if w is less than minus 1/3, and I don't have any room, it is divergent when I extrapolate back to 0. Okay, so divergent. So for matter and for radiation, d of t is equal to 3t and 2t respectively. So what inflation is a theory where I have some sort of accelerated expansion a double prime greater than 0. And let's take a simple model of this where a double prime over a is just constant. So this is de Sitter space. This is a prime over a. So derivative with respect to proper time. Okay, and so if you solve for what a of t is in this case, well, this is an easy equation to solve. It's just an exponential. And so we get e to the h t minus t naught. Okay, so now if I go to conformal time coordinates, if I make the shift between conformal time and proper time, let's see what it does to augment this diagram now. In conformal time, a of tau is 1 over minus h tau. Okay, so now, wait, we can start drawing things before tau equal to 0. So let's draw the new diagram. So here's 0, tau equal to 0, tau. Here's our picture that we were worried about. Okay. But now if I can keep on going backwards to progressively more negative tau, then I can keep on drawing these lines. Yes? And now I have just some cutoff point, some very small, tiny value of a, say a initial before inflation, before this sort of de Sitter-like evolution takes over. Then we have, maybe just before tau equal to 0, some a of sort of minus epsilon, a tiny little time difference before getting here. And okay, a tiny little difference here, a plus epsilon. I don't want things to diverge, right? So I'm sort of cutting things off. Because we know that there's some sort of physics that happens in between the epoch of inflation and Big Bang cosmology. So if you like, inside we have reheating, physics to be specified later. And now, when we draw these light cones backwards, we see that our initial conditions at this very early time, when the universe was very, very, very small, that I can correlate non-trivially what's going on here versus what's going on here. So I can establish non-trivial correlation functions because these points actually were in causal contact if I had this accelerated epoch of expansion, this epoch of accelerated expansion. Okay. Sorry, I can't hear you. Yeah, that's right. So I've just been able to go back further in time because, again, I'm avoiding the singularity. That's what I'm doing by putting sort of an A plus epsilon here. Because I have a toy model, right? This is just pure de Sitter evolution, and I'm not specifying how I get from that epoch of pure de Sitter evolution to the epoch where we've got matter and radiation and all these things sort of put back into the mix, okay? So what I have to do is I have to sort of cut off the theory a little bit before the would-be M-Planckian temperature Big Bang, and then sort of restart it, stop inflation at some point, and then restart the evolution afterwards. And so again, this picture will be a little bit different with an actual model of reheating. There'll be a way to sort of stitch these together, some different sort of epoch of evolution of the scale factor. But nevertheless, this is morally the right picture, okay? So again, this is sort of a toy model, but it gives you the answer that we're getting at, that you can solve the horizon problem with this kind of physics. The basic thing is I just correlate these 2 points by having them be in causal contact with each other in the past. Yep.
But considering, so now you get negative conformal time, and this comes only from considering the Sitter spaces.
So it will work for any model of inflation that we'll consider. It's just, how do you get the minus sign? You solve the equations and you figure out, what the actual evolution of the scale factor is in your model. So if I have a period of inflation, it will be a lot like that evolution there with a small, difference due to, say, a slow roll parameter that slowly changes the Hubble rate as a function of time.
Yeah, but my question is, what has changed that we are able to go beyond the singularity and consider negative conformal time?
So again, we're avoiding the singularity kind of in between here with some kind of physics to be specified, and that physics is the physics of how I exit inflation, so where I leave the slow roll regime, and where I then repopulate the matter, the universe with stuff, with matter, right? And so once I specify that physics, I can give the details of what's actually happening in this regime here. So tau equal to 0 will not correspond to a singularity in that case, okay? So I think that's maybe what you're getting at. You're still worried about Yeah, so it won't be 1 over tau when I do the right physics, you know, at this point there. Good. Okay. So now let's get away from the de Sitter limit and start to put in a more realistic picture of how this might happen. So what does slow roll inflation look like? I add a new scalar field, and it doesn't need to be a fundamental scalar field. I'm not specifying, you know, where this scalar field came from. You know, maybe it's a moduli, you know, maybe it's some sort of Goldstone boson with a shift symmetry. That's to be determined later. So let's just say that we have some v of phi, and maybe just one sort of direction I can go in field space in some very interesting sector that I might add up here. And we can sort of draw a toy picture where I draw the potential of this v of phi like this. And what I do is I imagine that there are some initial conditions set, you know, way back here, again, not specifying the physics of how those initial conditions did this, that leave the scalar field at some point high up on this potential. I've got a big universe. Maybe somewhere in that big universe, the scalar field is up here, and it leads to this epoch of accelerated expansion in that region in the very early universe. And now there's some gradient to the potential, which means that once the field is put there, it's going to start slowly rolling down this potential. Phi will evolve with time. So here's phi, and phi is just rolling down. So I'll call this like phi initial, and then phi will roll down, and then at some point the potential is not very flat anymore, so the scalar is going to start picking up sort of field velocity, and it'll run down here. I'll be exiting slow roll inflation. The scale factor evolution will not look anything like this anymore, and perhaps this inflaton oscillates around in the bottom of this minimum here. Perhaps it's coupled to some other fields that then damp this oscillation at the cost of producing those particles that the inflaton is coupled to. Okay? So here's a toy model of slow roll inflation followed by an epoch of reheating driven by the oscillations of the inflaton field. And it is the value v of phi I that will set the effective Hubble rate during inflation. That is, if you again go to the Friedmann equations, Hubble squared at phi I, if this thing is not moving very fast, is going to be approximately 1 over 3 m Planck squared times the energy density in the field, which is purely in the potential. Okay? And so then we get this period of accelerated inflation that is pure de Sitter if phi doesn't roll at all, if it just sits there, at least classically. Quantum mechanically, there are very interesting things there, but we'll get to that later. Okay. Yes? So again, I can't quite hear you from here. Yeah, so I'm saying that the field is just static at that point, so there's no energy density in the kinetic term. We're going to write out the full thing now. So just so you can plausibly see that this will lead to something like this picture here, that's what this is to convince you of. So if the field's here, it's not going to move very fast. Yes, especially when you take into account the expansion of the universe, which gives you a Hubble friction term that we're going to write down. Okay. So what is the action for a simple scalar field minimally coupled to gravity? So I keep on mixing up minus signs because Bauman uses the wrong sign metric convention. So bear with me with some of the minus signs if I might write them down wrong from time to time. Minus 1/2 d phi squared. Oops, I forgot the root g. Minus v of phi plus m Planck squared over 2 times the scalar curvature. And the stress energy tensor associated with the scalar field phi that's got to appear on the right-hand side of Einstein's equations. T mu nu is d mu phi d nu phi minus g mu nu. I think I've got this right. Again, don't trust signs. Okay, and so this is the stress energy tensor for this scalar field at any point in its evolution. Question?
In the axial, I think that is minus g. In the axial. Root is square.
Oh, yeah. Always implied. Very good. Good. Okay, and so if we now do this in proper time, so I haven't specified the coordinates here, so I'm switching back and forth between conformal and proper. If we work in proper time, we have T00 is minus the energy density in phi, and this gives us that the energy density in the field phi, we know this is just the Hamiltonian for the scalar field, right? This is going to be 1/2 phi prime squared plus v of phi. And similarly, p of phi is going to be the same thing, but with a minus sign, the Lagrangian density. All right, and so now we can write down an effective equation of state for every point along the field trajectory of this field phi as it moves down this potential. So what is the equation of state parameter? W is p phi over rho phi, which we just plug it in, phi prime squared minus v of phi, phi prime squared plus v of phi. And now if we look at this in its different regimes, we see that W will span the range between W equal to 1 and -1. In fact, that's the full range over which W's make any sense, is -1 to +1. So if you did the homework, there's a speed of sound issue in the fluid if you try to take W greater than 1. And it turns out there are unitarity issues if you try to take W less than -1. So this spans the whole range. Where W equal to -1 is when this term is potential dominated. That is when the kinetic energy in the field phi is subdominant. And in the case when the kinetic energy dominates, you go all the way to W equals +1. Okay? But crucially, -1 is less than -1/3, which means that we can achieve a period of accelerated expansion with this. Okay, so that makes us happy. By the way, -1/3 is sort of a special point. There are different energy conditions, strong energy condition, weak energy condition. When I take W less than -1/3, that is a violation of the strong energy condition, which is basically that on a time-like trajectory, if you're an observer on a time-like trajectory and you calculate the trace of the stress energy tensor, the strong energy condition is that the trace is positive, okay? And now here, the trace, if it's less than -1/3, is going to be negative because it's, rho plus 3p, right? That thing that showed up in the calculation of A double prime was precisely the trace term. I haven't gotten it all straight enough in my head right now to go through it right here. I'll just say that there's a strong energy condition, and it is curious that if I want to have this be the model of what leads to a better causal structure to explain the things that we see, the universe needs to violate it. Okay? So if you believe this story, you disbelieve in the validity of the strong energy condition. Okay, and now, so we can use all this information along with the scalar field evolution equation to get us the dynamics of what happens during this evolution. What we often do is we use some figure of merit to say how long do we stay in this region and how close to de Sitter space is the evolution during sort of this epoch of the field trajectory. And so we saw that the slowest roll is when h is constant. That's just pure de Sitter space. So a nice figure of merit might be a dimensionless combination of the time derivative of the Hubble rate, which if I'm going down, this minus sign is going to make epsilon positive, minus h divided by h squared. Okay? And if I take all this information here and I shove it into the Friedmann equation, taking into account the extra pieces of the stress energy tensor here, you can calculate, and maybe that's a good homework problem, that minus h prime over h squared is a function of the scalar field time derivative divided by m Planck squared times h squared again. Okay, so it's just evaluating h prime given the Friedmann equations over here. Okay, and so this is a nice figure of merit for how slowly am I rolling? Okay. If we actually want to get a picture where we are able to correlate disparate points on the sky, then I need to have this happen for a sufficient amount of time. That is, there's a beginning of inflation down here, there's an end of inflation over there, and I need some amount of e-folds of inflation to occur to solve the horizon problem, and also the flatness problem. So the rough figure of merit is 60 e-folds is enough to explain what we see. So how do we test if a particular model of inflation gives us enough e-folds? So here's a model, but I didn't specify a potential, right? But say I give you a potential, and you want to figure out where do I need to put phi in the beginning for a given potential in order to get this picture to work out for some given model that you've got. To answer that question, you want to know what the scalar equation of motion is. And you can either work that out directly from the action principle, from that action, or you can combine the Einstein equations as well, the continuity equation that we saw earlier on and that maybe you worked out for your homework. Phi double prime plus 3 times the Hubble rate at a given time, phi prime plus dv by d phi is equal to 0. Okay? So now for sustained slow roll, we don't want to go too fast down this potential, right? We don't want to go down like this, right? We want to be sitting up on top of the potential for long enough to get the required 60 e-folds of inflation. So to get sustained slow roll, we require that phi dot not go too fast and stay not going too fast for a while, which means that the second derivative of phi can't be too big. Otherwise, if I start off slow roll, I'll get off of slow roll too quickly. And again, there's a figure of merit. We want phi double prime to be less than the other term in the scalar equation, 3h phi prime. And when this is the case, then 3h phi prime is going to be approximately minus dv by d phi. Okay? So when this is the case, when this inequality is valid, we have an approximate equation for phi prime. And so here is our second slow roll condition, which can lead us to create a second slow roll parameter. And in order to have sustained inflation, we want both of these slow roll parameters to be small. you can turn the crank on sort of messing around with these relations that allow us to write these conditions in terms of features of the potential locally wherever I start the field phi. And that should be valid the whole time that phi is evolving during inflation. We want the slow roll parameters to stay small enough. And people now often write them. And this is a convention. You just want these to have the right conditions baked into them, basically. We have m Planck squared over, we have epsilon v, which is m Planck squared over 2 d log v by d phi squared. And in order to be in slow roll, we want this to be less than 1, and ideally significantly less than 1. And eta v, so v is the potential, that's why we're, so given a potential v, these are the slow roll parameters, m Planck squared, and then the absolute value of the second derivative of phi, the second derivative of v with respect to phi. And then, again, over the magnitude of the potential v. So this is for successful inflation. And if you want to check if a given model of yours works, you calculate the number of e-folds as a function of the field phi, where it ends up, which is equal to the integral over a from, let's see, a to a exit inflation of d log a. And looking at time, I'll just write, again, the answer that you can get out as a function of these slow roll parameters. And this is an integral over phi until phi exit of 1 over root 2 epsilon d phi over m Planck. Okay. And so you can work out the example for maybe the simplest model that you might think of for inflation, which is just that v is 1/2 m squared phi squared. Okay. Now the slow roll condition works out to be that phi e, so the initial condition is rather curiously root 2 times the Planck scale. And in order to get enough slow roll here, we need to start phi high enough on the m squared phi squared potential. So we need to start phi at some other value, which if I want to get 60 e-folds out of this integral, if I want to get 60 on the left-hand side, then I need phi initial to be greater than about 15 m Planck. So this is a little bit disconcerting. If I were to think as an effective field theorist, I'm not supposed to have an occupation number of my field that is in excess of, when I think about it in terms of an energy density, because phi carries mass units, exceeds that scale where I have no idea what's going on, right? Sorry. This here? So this is from working out the slow roll conditions by the end of inflation. So slow roll needs to be maintained, and so the slow roll condition is violated where it's not less than 1 anymore, because I can need to evaluate the slow roll parameters at all the points on the evolution of phi. I start it out here, and it ends down here. And so the question is, where does it end? It ends when the slow roll conditions are violated. And so we just plug and chug with this potential in here when we figure out what value of phi corresponds to this. Okay? And it doesn't depend on the mass squared. So here's phi initial. Here's phi final or phi exit. And yeah, we need to take it bigger than m Planck. Daniel seems to insinuate in his lectures that maybe we effective field theorists shouldn't worry about this, that string theorists have some answer of how to get sort of trans-Planckian field values. But as an effective field theorist that doesn't want to have to specify all the additional degrees of freedom in the theory, I probably shouldn't write down just this. I've got to write down the whole kit and caboodle, everything that's going on that gives rise to this kind of dynamics. So you probably need a complete theory. Okay. And now, this is another hierarchy problem, by the way, that we should worry about, unless we do specify something about the origin of the inflaton. That is, we're asking that the second derivative of the potential at some point be small, but we know that if we draw quantum corrections, if there's any particle in the game at mass scales above the mass scale of the inflaton, then Csaba's been telling you that quantum corrections are going to try to drag up the mass squared term up to that next nearest scale, okay? And so let's say at that scale you fix all the problems, it's like some supersymmetry or something. You're still going to have a little hierarchy problem between the mass of the inflaton and the dynamics of that other sort of spectator field that's there, but still couples to the inflaton and has non-trivial influences in terms of the quantum corrections in the theory. So you might worry that I've solved these hierarchy problems with another hierarchy problem and rephrased it. But the hope is that we do come up with a way to protect the inflaton mass with some dynamics that perhaps leads to a shift symmetry or an approximate shift symmetry for the inflaton that maintains these slow roll parameters. Okay. And so that's referred to as the eta problem by cosmologists, not to be confused with the eta prime problem in QCD. Here, eta is needs to be small, and the eta prime mass problem was that the masses were actually too big, and so they're sort of opposite to each other. And the answer had to do with non-perturbative contributions in QCD and anomalies. Question?
Could you explain a little bit more about the folds of inflation? I never get it really, and I always think that the 60 number is very arbitrary, and I don't know if you have a better explanation or intuition, I don't know.
Let's see. So I guess we want to calculate the number e to the 60, and we want to take the size of the angular size of the horizon that we thought should be that would be the horizon at recombination. And now what we want to do is multiply that by the e-fold factor, right? And so that E-fold factor is probably roughly the thing that gets me from 1 degree out to 180 degrees. So I think that's roughly kind of the way you can think about that figure of merit. Yep.
The slow roll parameter should be evaluated in a characteristic field value?
So they need to be evaluated at every point along the inflaton trajectory. So if we want normal inflation to be happening at every point in the evolution, we want these slow roll parameters to be slow roll during that epoch. Okay? I mean, maybe there's a little violation for a little while during that time, and maybe that imprints itself onto the power spectrum. That was kind of the toy model that I showed you on the first day, and that would have interesting implications for the power spectrum. But the idea here is that we're presuming a simple inflation model without that sort of extra stuff that maintains slow roll along the whole way. And so there might be some constraints by looking at the power spectrum of how, over what period of time can I actually maybe violate slow roll parameters during inflation, things like this. We can get constraints on that sort of dynamics by looking at the CMB, as we've been saying. Okay, not protected by any symmetry, good. Okay, so that is classical inflation. You can pick different potentials here that maybe you don't have this kind of nasty feature under it. You can just stick in your favorite V and get out the dynamics of your classical inflation model. However, what we've said so far has nothing to do with the non-trivial initial conditions that we're now measuring by looking at the CMB and tracing back to when those seeds, those perturbations re-entered the horizon, right? So we want to now start to get an idea of how those perturbations are arising in the model of inflation. So right now it's just classical rolling. Next, what we want to consider is what happens when we add quantum mechanics to the mix. So before I do that, maybe this is a good time to just ask questions, because next will be time for something completely different. Yes, oh, there's two up here.
Yeah, so this potential is like just m square phi square. So let's say if I want to add matter and radiation field too, so do we add those standard model field here or like later stages some?
So then that you're talking about that dynamics that happened in this region here, and that is another arena for interesting model building. So that is not part of this picture here. And probably this, again, I'm not an expert in this field, but I would guess that this doesn't reheat very well because this mass needs to be very small, and so probably the oscillations of this m squared, phi squared inflaton are not sufficient to reheat the universe. So I need something else to happen to the potential here in order to get repopulation of the universe that gets me from inflationary-like dynamics to matter and radiation-like dynamics. So that is not in the picture, the radiation and matter that we're discussing now.
So in the very beginning of the lecture, you wrote down that we have a contribution to the Hubble parameter that goes like the curvature over a squared, and we want to get rid of this. That's why we invented inflation, to make a very big so it drops out.
Yes. So I've actually just left the curvature out in this whole thing. I guess you could put it back, and that would lead to, you at least want the inflaton to dominate at late times enough that I actually get an effective equation of state that is -1/3, right? So I guess So if I add this dynamics and curvature, inflation won't happen until the spatial curvature is diluted enough that until the energy density is dominated by something with W less than -1/3, right? So I have some early stuff that then transitions to the epoch of inflation once curvature dilutes by enough. And then we enter sort of this story here.
No, but the thing I was wondering about is that we had the matter and radiation terms that actually go with, are suppressed by higher powers of A. So if we want to get rid of curvature, we will also even faster get rid of all our matter and energy density.
But that was before inflation. So that's some big question mark. You know, what is actually going on before the epoch of inflation? So that there was not our matter and radiation that we see today. It was something about the initial conditions before inflation. So I imagine what's going on before inflation. I start diluting all the stuff until I'm left with something that looks like pure vacuum energy or almost pure vacuum energy. That is this potential term V of phi.
Okay, and like the ordinary matter and radiation we produce then in this oscillatory phase of the inflaton, like when it decays?
That's right. And again, that's a toy model. You know, you need to actually write down your realistic theory of reheating that does things right. And again, there are influences of reheating on the things that we see today as well. You need, and we're not going to go over reheating. We only have 1 week, so that would be an entirely different week's worth of lectures, I'm sure.
Okay, thanks.
Any other questions?
So I understand that we are going to use the slow roll and to search for new physics, and we are going to talk about it later. But I was wondering if there was another solution to the problems like homogeneous and isotropic that answer this, and the flat and the relics, but it's not inflation. So I was curious about that.
Yes, there are attempts to solve these problems without inflation. And so I'm going to speak without super confidence, just sort of like anecdotal. I think they often give a larger tensor to scalar ratio in CMB, in the CMB power spectrum, and that I'm not sure that if they're ruled out or not, but they might be kind of on the threshold. I don't know enough to speak confidently about what those models are, but there are people working on alternatives. Robert Brandenberger, I think, is working on these, and maybe Steinhardt. Was Steinhardt? I think Steinhardt is looking at alternative models as well.
For a while. I don't know if he still does. But,
right. So if you want to take a look at alternatives, those are a couple of folks who have been pushing in that direction. Yeah, that's about as much as I can say, is maybe just give you a way to start looking through the references.
Yeah, I think, these two names, if you Google Steinhardt, Paul Steinhardt, these are adamantly anti-inflation, like the central bank of physics.
Okay, so I'm going to move on to the next point. We can certainly, we'll have the discussion session this afternoon, and we can chat. So, but I do want to start to get to the super interesting part of things, which is how this model, without adding anything except what we know has to be there, quantum mechanics, gives rise to not just perturbations, but perturbations like the ones that we see, perturbations that are approximately scale invariant. And eventually we'll see how variations on inflationary models can give different predictions for other observables that we're trying to probe now. So we're getting to the point where we can start to rule out various models of inflation, and it's always a dubious pleasure to have your model killed by data. But now we're now entering an era where we're killing off huge swaths of parameter space with the data that we're getting. Okay? So before talking about the quantum mechanics of inflation, I want everybody to remember what they learned in kindergarten. That's the usual joke, right? So recall what we learned about quantum clocks. And this brings to bear on the energy-time uncertainty relation. Where delta E, delta T, delta E is less than h bar over 2. Oh, it's greater. Okay, this is a weird relation because there is no T observable. There's no T operator. There is an energy operator, the Hamiltonian, but there is no time operator in quantum mechanics. And this means that if we want to have this relation make sense, then we have to have some observable in our quantum mechanical system that sort of stands in for the time observable. Need sort of an ancillary clock. And so let's say that observable corresponds to an operator A. And if this is going to be any kind of useful clock in the kind of system that we're looking at, there's got to be some time variation in the vacuum expectation value for this operator. That is dA by dt can't be equal to 0. And if this is the case, then we can write this energy-time uncertainty relation using the uncertainty relation between A and the Hamiltonian, where the variation, the statistics for A times the variation for the statistics in the energy divided by dA by dt are the stand-in for the energy-time uncertainty relation, okay? 1/2. Okay? And so now, what is our classical inflationary model? If I'm to think about it in terms of a quantum mechanical system, the classical value for phi should correspond to the vacuum expectation value of, so the vacuum expectation value of phi will correspond to the vacuum expectation value of A, and the time variation of phi lets us use the field phi as an ancillary to T. So the inflaton serves as a quantum clock for us. Okay, and so that means that we can think about phi as an observable that has some statistical variation. So now a quantum field operator phi and it has a minimal variation determined by the uncertainty principle. Okay? So now our inflationary picture is augmented, roughly speaking, by a time variation in the expectation value and then a quantum mechanical variation about the expectation value as a function of time. Okay, so we can envision these as quantum fluctuations of the inflaton that have some minimal statistical variation. And so now what we want to do is use quantum mechanics to get a prediction for the spectrum of these fluctuations. We want to quantize this system. Okay. So now our picture here is, now how do we quantize things? First, we write our field. So we're just doing classical right now. We write down the classical system. We write down the classical system's action, and then we canonically quantize. We find our coordinate, our conjugate momentum. We impose uncertainty relations. And then once we do that, we can gather statistics given some condition for the initial state that we begin with, and then time evolve. All right, so phi is an average value of phi of t plus fluctuations around that background that we wish to quantize. So if you like, we've got a vacuum expectation value and fluctuations. All right. And now, roughly speaking, once we measure the system, once we look at it or anybody looks at it, we project the quantum superposition of states onto some particular picture of fluctuations that we see, with their variation governed by the quantum statistics. Okay, so now we perhaps immediately see something that makes us a bit scared about approaching this problem, is that this isn't the only thing that's fluctuating in the game. So we have a theory of gravity plus a scalar field, right? And now we know how many degrees of freedom there are in this picture. There's two gravitons, two polarizations for the massless graviton, and then there's, of course, the degree of freedom in the scalar field. But when I couple the two of these systems together, there is going to be a mixing between the degrees of freedom that are appearing in the metric and this scalar degree of freedom. So there's going to be a little bit of a challenge to identify what is the actual physical degree of freedom that I need to quantize. Okay? So today, in the last 5 minutes, we'll look at a simpler model first and build up to the more complicated picture where I take into account the mixing between this fluctuation and the fluctuations inside the metric. And there's an added element to the mix that really makes us want to do something simpler first, is that we need to learn quantum mechanics in this curved background, right? There's a background that we're expanding around that depends on time, and so a lot of the things that you learn about quantum mechanics, presuming time independence, are going to be violated in this case. Okay, so we need to do quantum mechanics in quasi-de Sitter space, so almost de Sitter space. A here was just some operator, so I'm just reminding everybody how we measure time in quantum theories. It's that we have some ancillary observable that's actually ticking time for us, like the quantum clocks at NIST or whatever, some oscillations of some cesium atoms. Yeah. Okay, so let's start, as I said, simpler. Let's ignore the complication of fluctuations of gravity. Which means for a scalar field, we're just going to be studying a free scalar in the background geometry, which for the moment we'll just say is de Sitter space. So free phi in de Sitter, which has in action -1/2 integral of d for x. We got to take the root g's because there's a background de Sitter evolution, g mu nu, d mu phi, d nu phi. And we can expand this out as in de Sitter space, or just a FRW metric, I guess, for now, phi dot squared minus di phi squared. Starting with massless, we can add a mass term at the end, so this is just an easier place to start. Now, we all remember that we like to canonically normalize our fields before we go about the process of quantizing. It's a convention, but it just makes things easier, especially when our normalization is time dependent. And so if we take a new field V, which is A times phi, you can check that if you make this field redefinition, this action becomes the following. V dot squared minus div squared, and then a time-dependent mass term. Okay? And in particular, for de Sitter evolution, A is -1 over h tau. So we know what to stick in for this mass term, for this effective mass term. It's just 2 over tau squared. Okay, so now when we work out the equation of motion for V, like we were all taught how to do, then we get an equation of motion for, and again, let's expand in Fourier modes. So Vk carries some time dependence plus k squared minus, in our case, 2 over tau squared. Okay? And so this is almost like what you learned how to do in your quantum field theory class, except for the fact that there's this time-dependent mass term in the game. But let's think about what this looks like at an early epoch, right? So near the beginning of inflation for some fixed mode number, so say I fix k, but now I think about very early times, which correspond to minus infinity in this epoch of de Sitter evolution, then it just looks like the usual wave equation in flat space, okay? Now this makes sense. We know that when I look at a curved manifold, if I look close enough, then the manifold looks flat. So if I look at a mode number with very short wavelength, that mode doesn't know that there's a net curvature in the system, okay? So small mode numbers don't know about this. And any mode number, if I consider early enough times, is small enough. Okay. I do have to wrap up so that we can continue tomorrow. So let me see if I can find myself a good stopping point. Let me just say, I guess, what the plan will be. We need to quantize these modes which means we need to get the solutions to this equation that's been promoted to an operator equation. Okay? And ideally, since we know that this thing is just like oscillators, we want to have annihilation and creation operators for these modes. So we want to have an AK and an AK dagger. We want to write down the corresponding Hamiltonian. And we want to then figure out how to disambiguate between the fact that V of k is going to be a superposition of these operators, or the addition of these operators, something like Vk of tau A k plus Vk star tau AK dagger. And now there's a give and take between how I've defined these A's, right? I could absorb A into V and vice versa, yes? And so that ambiguity between how I define the operators A, once I impose commutation relations for them, is going to come to bear on the initial conditions that we choose at the beginning of inflation. Okay? And that's going to be identifying the vacuum, which then sets those initial conditions. And a nice set of initial conditions, given that at early time, every k is a simple harmonic oscillator, is to choose those initial conditions such that all of those oscillators begin their life in the ground state of the effective simple harmonic oscillator equation that very well approximates what the mode is doing at that early epoch. Okay, and that's called, when we do that and we then solve for what that means for the initial conditions on V, that is the identification of the Bunch-Davies mode function. Okay, so I just said the words. I'll say them again tomorrow, and tomorrow you'll feel like, oh yes, I know exactly what he's talking about because he said that yesterday, and we'll specify exactly what that procedure is. Okay. All right. That's it for today. Thank you.
Okay, I remind you all that today afternoon we're going to have a discussion session, so you can research some of the questions if you want.